Most of us probably remember that matter can be classified as solid, liquid, gas, or plasma based on the kinetic theory of matter. Probably remember solid, liquid, gas, maybe not plasma. But this kinetic theory of matter states that all particles of matter are in constant motion and are affected by the forces of attraction between them. Also, the more kinetic energy a substance has, the faster its particle moves. And we can describe our solids, liquids, gases, plasmas based on this theory, and even a Bose-Einstein condensate, which is a brand new state of matter we're going to talk about. So first up, we've got solids. They have a fixed shape, a definite volume, and those particles are tightly packed, touching each other in an ordered arrangement. Now, even though you can't really feel it, these particles are actually they're moving, they're vibrating. There's only one point in time where this does not happen, and that is if you reach a temperature of absolute zero. That means there is no kinetic energy, no vibrations. That has not been accomplished yet here on Earth. Liquids, on the other hand, do not have a fixed shape. They take the shape of whatever container you put them in. There is a definite volume, though. If you have 2 liters of liquid in a 2-liter bottle and dump that into a ginormous jug, it'll still be 2 liters of liquid. It will just take the shape of that jug. The particles in liquids are in constant motion, and there are attractions, but they slide past each other, and that allows liquids to flow. Gases don't have a fixed shape or a definite volume. They get both of those from their container. You put air or helium in a balloon, it fills the balloon to whatever volume and whatever shape that balloon is. But gas particles are very far apart, and they rarely touch. They are also in constant, rapid, random, straight-line motion, and they bounce away from anything they collide with, other particles, or even the container walls. Gases also flow and are easily compressed. You can squeeze a balloon and cause those particles to go closer together. Plasmas, while we don't know or see or talk too much about them here on Earth, they are the most prevalent form of matter in the universe. They exist at extremely high temperatures, where the atoms essentially come apart and it's just a big stew of particles. One way to think of them is they are like super hot atoms. Super hot atoms. Now these Bose-Einstein condensates, they are relatively new. They are the opposite of plasmas, occurring near that temperature I mentioned earlier, absolute zero. They were finally created in the lab in 1995, not too long ago. This is nearly 80 years after they were first predicted to exist by, yes, Einstein and another scientist, Mr. Bose. At such a low temperature, atoms lose their individuality, and unlike plasmas where they come apart, they come together and become one superatom. So essentially, they're kind of like the opposite of plasmas. Those are, I said, were super hot atoms. These are super cold atoms. Now, to change phase, you must use heat. Heat should either be absorbed or released. Melting, I hope you remember, is when a solid changes to a liquid. That means the heat is absorbed by the solid. Freezing is the opposite of that. Heat is released by a liquid, changing it into a solid. Easiest thing to think about here is an ice cube. When it's exposed to the warmth, a solid piece of ice absorbs the heat, melts into liquid water. Whereas when you put liquid water into the freezer, that liquid releases heat and changes to an ice cube. Vaporization is when a liquid changes to a gas through the boiling process, so the heat is added to the liquid. Evaporation is the same thing. Liquid is changing to a gas, but this happens below the boiling point. So obviously when there's a rainstorm on a summer day and puddles are left behind, the puddles don't boil away, they evaporate. And then condensation is the reverse of this. Heat is removed from a gas, changing it back to a liquid. like steam condensing on a bathroom mirror or on a window in the winter when you're cooking spaghetti in the kitchen. Two changes of state you might not be as familiar with are sublimation and deposition. Sublimation is when we go directly from a solid to a gas. So heat is added to that solid, changing it to a gas, like dry ice. The opposite of that is deposition. Heat removed from a gas, changing it to a solid. The moisture in the air on a winter's day can then be deposited as frost on a window overnight when it gets much, much colder. So here you see a little diagram reflecting these states of matter and changes. So you can see here is a solid, add heat, turns to a liquid, add heat, gas, add heat, plasma. And then obviously going backwards would be the removal of heat. And you could also, here's a little picture, I guess you would call this the Bose-Einstein condensate. Then solid, liquid, gas, plasma. If we add in our new little buddy there. So now we can sum this up on a phase change diagram. And you'll have one of these to practice with, but here we can see some interesting points on the phase change diagram. So here we have seen that I've added some interesting, for me, some important labels. This is a diagram of temperature versus heat energy going in. So as the temperature is going up, obviously heat energy is being supplied. As you'll see on your practice paper, you can also look at this as temperature going up over a period of time. But it's the same diagram. So we see our three main phases of matter on planet Earth. Solid down here, particles close together, low temperature. Liquid here, particles a little further apart, warmer temperature. Gas up here, particles a little farther apart at a higher temperature. So there's been labeled solid, liquid, gas. And then the arrows representing the phase changes between them. A solid to a liquid is melting. A liquid to a gas is vaporization. Backwards, gas to liquid, condensing. And down here, liquid to solid, freezing. Ta-da! Magic! And now you can see that I have added some important points. As we travel up the temperature, a solid turns into a liquid. That is the melting point. As we go backwards, a liquid turning to a solid is the freezing point. Same thing up here. Liquid to gas. Right here is where the liquid starts to boil, boiling point. Gas back to liquid, condensing point. Very important to note here that these points are at the same temperature. So freezing and melting happens at the same temperature. Boiling and condensing at the same temperature. It just depends if you're going up or down. Water, as we know, on the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and melts at 32. Just depends, like I said, is it getting warmer or colder? The other thing you notice is that during a phase change, the temperature stays constant. So an ice cube gets warmer and then all of a sudden it starts to melt. The temperature stays the same until it is completely done melting. And then the temperature can start to go up. Same here. Put water on the stove to make it boil. It heats up, heats up, heats up. And then as soon as it starts boiling, that bubbling water on the stove never gets any hotter. It stays the same. And then steam is at a higher temperature because it has more energy. I believe that is all the information you will need in order to complete that practice paper. Yes, so enjoy and have a wonderful weekend, and I will see you Monday.